All right, next I'd like to look at center of mass problems. Now, so far what we have assumed in all of our previous examples is that the masses under consideration have had zero size. We haven't considered rotation or anything else involving the spatial extent of these masses. But if we allow for the possibility that the masses are distributed over a certain volume, then we do need to consider the idea of center of mass. And so, put simply, we can think of the center of mass as being our balance point in 3 dimensions. And so, in other words, if I take this meter stick and I balance it this way, then it should balance around the 50 centimeter mark. Then I could also balance it this way. It should balance around pretty much the geometric center, this direction. Then if I could balance it this way, I'm going to have 3 different lines that intersect for this 3-dimensional problem. That line, this line, and so we're going this way, we're going through, let's say like that, and then also in this direction, straight through. Then all 3 of those lines are going to intersect in one point. And that point is going to be the center of mass point for that object. Now, why are we interested in center of mass? Well, it's important for a number of different reasons. One reason why it's important is that for many problems, you can consider all of the mass to be concentrated at the center of mass position. And you get the right answer if you do that. So it's a nice little trick that helps you solve problems. So, and it's going to be hard for me to do this in this video if I actually throw this thing. But let's just kind of slow it down a little bit. Let's imagine that I'm throwing this meter stick in such a way that it rotates like this. Okay. And while I'm doing that, I want to determine the motion of the meter stick. Well, pretty clearly, if I try to follow a point that's on the edge of the meter stick, it's going to be doing some very complicated kind of motion. However, if I follow the path of the center of mass, it's exactly the same motion that a point mass would take that follows that same trajectory. Okay? And so I can simplify the problem by pretending that all of the mass is located at the center of mass position. Then I simply have a parabolic trajectory of the center of mass superimposed on uniform circular motion. And so now I've broken the problem down into 2 simpler problems that can be solved. Okay, so that's one good reason for using the center of mass. Another really good reason is that in a closed system, the center of mass moves at constant velocity. So in other words, let's say that we had those 2 cars that we were talking about before that are moving along like this. And one is moving toward the other, and then they collide together, and both cars move off at some angle. We determined in that last example, check your notes for this, that the angle of deflection was 45 degrees. Well, we can figure out a balance point between these 2 masses at each point in the trajectory, and this would be the path of the center of mass. And the path at the center of mass, it being a closed system, is going to stay at a constant velocity. So even after the two have collided, the center of mass position is going to move at a constant velocity all the way through, because there are no external forces acting. And so you can pretend then that this is essentially the constant velocity of a center of mass that is not experiencing an external force. And so the external force is equal to dp dt. This is the momentum of the center of mass. Okay, and so this means that p center of mass is a constant, which means that you, in a closed system with no external forces, that's what closed means, is no external forces. So if you have no external forces, then the path of the center of mass follows a constant velocity path. And so that's useful too. Or if the velocity is 0, you could, for example, have a person in a boat that gets up and moves to the other side of the boat. Well, you can figure out how much the boat has moved in the opposite direction if you can figure out where the center of mass is, because you know the center of mass isn't going to move. Okay, so if this velocity of the center of mass is 0, then you can use that if the system reconfigures itself to figure out how much each component of the system has moved in order to keep the center of mass in the same place, assuming that v is 0. Okay, and so these are examples that we will look at different points throughout the semester. But what I'd like to do right now is just show how we could do a simple calculation to determine the center of mass. Well, let's assume that this system is one-dimensional for simplicity. Let's say that this point here is some point of reference. And then here we'll have mass 1. Say that mass 1 here is equal to 2 kilograms. And let's say that that's 3 meters away from our point of reference. Then let's say that mass 2 is 5 kilograms. And that mass is 5 meters away from our point of reference. And then let's find a third mass out here at 7 meters away from our point of reference. We'll call it mass 3. And we'll set that equal to 2 kilograms as well. So we have M1 and M3 at 2 kilograms and M2 at 5 kilograms. Let's find the balance point, or the center of mass, for the system. Okay, so first of all, we could use a little bit of intuition to see that if we could stick an imaginary stick through all 3 of these masses, and let's say that stick didn't weigh anything, and we wanted to find the balance point, I think you could probably agree that the balance point for these 3 masses would be located at the position of M2, because this one, the M1, is 2 meters away, and the M3 is 2 meters away. So there's equal masses on both sides, and so that the center of mass should be right at the location of our 5 kilogram mass, M2. But let's use the basic principles of how to solve for the center of mass in a system like this to verify our intuition. Okay, so what I'm going to do here is I'm going to say x center of mass is equal to the sum of m sub I, x sub I, divided by the sum of m sub I. Okay, so in other words, each of these masses is going to be weighted by how far it is away from our point of reference. So x of I then is equal to the distance of each mass, of the ith mass, I should say, from our point of reference. And the m sub I is equal to the mass of the ith object. And then we'll just divide that by the total mass of the system. And that'll essentially give us the average position of all three masses. And that would be our center of mass position in one dimension. Okay, now if we had a distribution in 2 dimensions, then we'd also need a y center of mass, which would have a similar kind of a mathematical form, but would deal with the y sub i's. Okay, but we'll just do this in 1 dimension. And so for this problem then, x center of mass is going to equal, well, m1 and then x1 plus m2 x2 plus m3 x3. That's our m sub I x sub I from I equals 1 to 3. And then we'll divide that by the total mass, m1 plus m2 plus m3. So that's the sum of m sub I from I equals 1 to 3. Okay, so now plugging in values from our point of reference, x1 is 3 meters, x2 is 5 meters, and x3 is 7 meters from our point of reference. 3, 5, 7. And so we have m1, that's 2 kilograms times 3 meters plus 5 kilograms times 5 meters plus 2 kilograms times 7 meters divided by 2 kilograms plus 5 kilograms plus 2 kilograms. Okay, so this is 2 times 3 is 6. I'll drop the units in this last step. 6 plus 25 plus 14 divided by, here we have 2 and 5 is 7 and 2 is 9. And you can punch out this number on your calculator and you get x center of mass is 5 meters. So in other words, what we've shown here is that the center of mass position is located exactly where we anticipated that it would be located. And so, in other words, we can pretend now that if all three of these masses remain in this configuration and we apply force to this system, then it would move in just the same way as if all the masses were concentrated at this one point. If we were to throw this thing as a baton and it had an imaginary stick sticking through it, then the center of mass at this position would move either with constant velocity if there's no external force acting, or in a parabolic path, say, if we threw it the way that we threw the meter stick. Okay. Now, in your math classes, you probably looked at integration problems that deal with center of mass. We will not be getting into that level of depth. In just about every example that I can think of, the center of mass will either be obvious to you or will be easy to calculate the way that I've shown here. Okay, so with that idea in mind, what I'd like to do is move ahead and take a look at our conditions for equilibrium in Chapter 11. Now remember, equilibrium has two requirements that we've looked at so far. The sum of the x forces is 0, and the sum of the y forces is 0 in a two-dimensional problem. But it turns out there's a third condition for equilibrium, and that is that the sum of the torques are equal to 0. Where tau is what we'll define as the torque. Okay, so we need to understand then what torque is, not only to be able to apply our third condition for equilibrium, but also to handle problems from chapters 9 and 10. Now we haven't started chapters 9 or 10 yet. We're doing chapter 11 first, and just the first 3 sections of chapter 11. We're not getting to stress and strain. Okay, and so the reason that we're doing that now is to give you a familiarity for torque, because I found that in the past people have trouble setting up torque problems. And so before we get to torque applications from chapters 9 and 10, we'll look at static torque problems and get you used to those first. So that's why we're going straight to chapter 11 right now. So what is torque? Well, put simply, we can say that torque is produced by a force that causes a change in the spin rate. Now you may remember we've done a lab where we dealt with spin rate, and that was omega. That's what we called our spin rate. So in other words, if we can change the spin rate of an object, then the force that we apply is generating a torque. Okay, and so let's look at an example. Okay, so here I am going to apply a torque to this chair. Okay, now where is the center of mass of the chair? I'm not exactly sure, but if I apply a torque to the seat, I can see that the center of mass is probably somewhere in here, not knowing exactly where. But if I apply a force, let's say like this, if I apply equal and opposite forces, we say the system's in equilibrium because there's no motion that is associated with this. On the other hand, if I apply equal and opposite forces off of the center of mass, then even though the sum of the forces cancels, the torque doesn't cancel. And so the system starts to change its spin rate. So what I'm doing here basically then is I am applying forces in such a way as to not change the motion of the center of mass, but to cause a rotational motion about the center of mass. Okay, so if we were to look at a problem like the following, let's say that we are trying to unscrew a bolt. So here's our bolt, screwed in tight, and so we use a open-end wrench, let's say, to do that. And so here at the other end of the open-end wrench, we apply a force, let's say off at an angle like that. You go, well, that's kind of dumb. Why are you applying the force off at an angle when it's pretty clear that you'd want to be applying the force perpendicular to the axis of the wrench. Because if you do it this way, you're going to pull, there's going to be a component of the force that'll pull the wrench right off of the bolt. And so you want to apply force in such a way as to maximize the turning or the change in the spin rate of this thing without moving it either this way or that way. And so this is why we're looking at the perpendicular component of the force when we deal with torque. So if this is our force, F, then we'll call this part here the part that generates the torque. We'll call that F perpendicular. And then this part of the force is the part that doesn't help us with the torque. We'll call this F parallel. Okay? And then let's call this distance here our radius vector r. Okay, so we'll define r then as the distance from the pivot point to the point of application of the force. So, of course, I'm going to want to apply my force at a distance away from the wrench that is as far as possible to maximize the torque. If I try to apply it here, then I'm going to get very little torque. And I'm going to hurt my hand trying to break loose this bolt if I apply the force here. So I want to make this distance as big as possible, but I also want to make the perpendicular part of the force as big as possible in order to generate the maximum torque. And so if we consider this angle here, theta, to be the angle between F and R, okay, so let's just redraw that over here where we put the tails of the two vectors together. Here's the direction of F, here's the direction of R. That angle is theta. Then F perpendicular is going to equal F sine theta. And so our torque then should be equal to R times F perpendicular, or RF sine theta, where theta is the angle between R and F. And so clearly then, I think you can see that this torque is going to be maximum when theta is equal to 90 degrees. And the torque will be a minimum when theta is 0 or 180. Because in those cases, you're either pushing the wrench right into the bolt, which isn't turning anything, it's just hurting your hand, and maybe snapping off the top of the bolt, or you're pulling this way, and you're just pulling your open-end wrench away, and you're not doing anything to cause the wrench to rotate. Okay, so this then is our general expression for the torque in terms of what we call the radius vector and the perpendicular component of the force. And so let's say we do the best we can now. We apply a torque to the system by keeping the angle of the force perpendicular to the radius vector. Oh, we just can't do it. Okay? And maybe even the open-end wrench may start to knock off the edges of the bolt. And so you go, well, what you need is a box end wrench. So that distributes the force more evenly around the bolt. So you put a box end wrench on here, and you go, hey, you need an extension. So you put a pipe on this thing so that you can get a greater radius vector. Now try it. Okay, so now instead of applying the force here, I'm going to apply the force at a distance 2r away. But I'm still going to apply that same maximum force that I could have applied before. In this position, I'm going to apply it here instead. Okay? So that should then, I think you'll agree, double the torque. And so if that's the case then you start to twist this thing. You hear a little bit of creaking here. Twist it a little more and snap! You break the bolt right off. It turned out it was left-handed threads. Okay. Whoops. Now we have to tap the block. But at least we had the right idea. We increased the torque, but we didn't realize that, that we were actually tightening this bolt and not loosening it. But anyway, that's the way that you would proceed to try to take care of breaking loose that pesky bolt. Now, similarly, if you are trying to open a door, opening that door is going to be easy if you apply your force. Let's say we're looking down on the door. Here are the door knobs. Notice that the door knobs are close to the edge of the door, right? And so then here are the hinges, and so this is the top view on the door. But does anybody grab the door and try to open it this way? No. Of course not. You'd have to be foolish to try to do that. Or you could push in this way, but that would just put stress on the hinge. That wouldn't open the door. The whole idea here is that you put the doorknob as close to the edge of the door surface as possible to increase your radius vector, and then you apply a force either this way or that way to maximize your torque and change the spin rate of the door so you can open up the door. Okay, so it's as simple as that. Things that we've looked at before kind of automatically are actually can be expressed in terms of this idea of a force that's acting through some radius vector distance from the point of application of the force and the pivot point in such a way as to make your change in the spin rate as large as possible.